called meta reinforcement learning with self-modifying networks. So, what's this paper all about? Let me start with a simple analogy. Let's consider the meta reinforcement algorithm as a delivery service, aiming to transport packages efficiently between locations. The task that we perform would represent delivering to different locations, like a home, office, or school. The delivery routes would be considered the policies for each task or a strategy for reaching each location. A good policy gets packages delivered quickly with minimal cost. The goal then is to find a flexible delivery strategy or meta policy that works well for various types of locations or tasks. Our challenge here would be that each location may have different terrain, traffic, analogous to different tasks in meta reinforcement learning that have unique characteristics. So the objective for meta reinforcement learning aims to generate a distribution of policies that are adapted to distribution of tasks. Here, the optimal policy refers to a distribution of policies. Each policy is adapted to a set of tasks, which refers to a different Markov decision process. We must find a transport plan that maximizes our reward metric R. However, finding the optimal transport plan is generally an intractable problem because the distribution of mu of the policies is usually unknown and has no explicit form. Therefore, we optimize a surrogate problem. The surrogate problem defines a parametric procedure that builds for any task a sequence of improving policies. We define data as a set of metaparameters that governs the evolution of sequence of policies and the distribution measure of the policy after learning task T during some period T. The expected outcome of meta reinforcement learning would be a high performance policy, a high learning capacity, and an improved generality. So, the research paper makes a reference to synaptic plasticity. Now, synaptic plasticity is essentially the brain's capability of increasing its neural connections speed from one to the other. When we have strong plasticity, it leads to fast plasticity, which in essence allows the brain to adapt, store, and manipulate information efficiently. In recurrent networks, we will utilize fast weights where connections between the neurons can change rapidly. This research suggests that using fast weights in the context of external rewards signals or the current state of the synaptic connection themselves. Now, this is what researchers call MET-ODS, which is a computational model that compresses an experience of a task into dynamic weights. MET-ODS stands for Meta-Optimized Dynamical Synapses and is theoretically presented as a model-free approach to performing stochastic feedback control in a policy space. The image shown here shows a layer of the MET-ODS which updates its weights by recursive applications of read and write operations based on neural activations V and synaptic traces W. The model receives continuous feedback in the form of environmental rewards, influencing the dynamic of the weight. This combination results in a recursive control scheme, allowing the model to develop a self-contained reinforcement paradigm. The weights in the network determine how information flows through the network, and how much flows through it is similar to the synaptic connections between neurons. The read operation involves linearly projecting neural activations through dynamic weights. This projection is followed by element-wise nonlinear operation, typically governed by a nonlinear activation function. This corresponds to the nonlinear response of a neuron population to a specific activation pattern. The write operation involves building a local weight update rule using element-wise weighting. This update rule is constructed through a product that emulates a local Hebbian rule, which is a biological concept where synaptic connections strengthen when two neurons are active at the same time. The model will utilize these read and write operations by performing a recursive update. This means that the operations are applied multiple times, and each time the updating the neural activations and weights based on the current and previous states. This recursive update captures temporal dynamics, allowing the model to mix information between the current neural activation and the previous iterates, effectively learning and adapting over time. As for the algorithm, we first initialize our metaparameters data and our dynamic weights. For each time step t in the learning process, we will generate an information vector v using a feed-forward function that embeds our states transition and previous reward information. For the states S in the set of states, we update the information vector based on the previous iteration of dynamic weights and update the synaptic weights using a combination of the previous weights and new information, incorporating the parameters k and beta. Now, k and beta are scalar values that are learned along with the plasticity parameters alpha and correspond to the delayed contributions of the previous patterns and synaptic states to the current operations. When done, we use a feed-forward policies function g to read out actions a of t and estimates v of t based on the final information vector of s. We then set the synaptic configuration for the next step w sub t to the final synaptic weights from the last iterations w of s. Now, the researchers will go over 3 different test experiments, and for these test experiments, they will utilize different meta-reinforcement models to compare their experiment results to. These models include model-agnostic meta-learning, reinforcement learning 2, and probabilistic embeddings for actor-critic learning. The first experiment task that they cover is a one-shot reinforcement learning scenario and rapid motor control. A one-shot reinforcement learning involves scenarios where an agent is required to adapt quickly and effectively to a new task or environment after just a single exposure. The top images show the Harlow experiment, where the agent selects between 2 variables with randomized positions, associating one with the positive and the other one with negative rewards. Even a small network of 20 neurons can solve this task perfectly with MET-ODS by adapting its policy in a few time steps. The bottom experiment is the Mujuko ant-directional experiment. The agent learns to produce locomotive policies in a few steps, outperforming models like MAML that require multiple episodes for proper adaptation. MET-ODS performs well with one-shot reinforcement learning, having its recursive Hebbian update combined with reward feedback. The study also tests meta-reinforcement models in a maze navigation task with randomly generated configurations. MET-ODS outperforms MAML and reinforcement learning 2 in exploration, excitation, and success rate. The experiment involves a partially observable environment where the agent must locate a target in the maze with reduced visual field and random positions changes after each reward encounter. MET-ODOS also exhibits generalization capabilities to larger mazes. The exact results also shown below. You can see that MET-ODS better explores the mazes as measured by the average number of steps before the first reward and the success rate in finding the reward at least once. It also better exploits the maze as per the accumulated reward. And finally, the study evaluates the generality of learned reinforcement programs in meta-reinforcement models, particularly focused on motor control tasks. Tests include dexterous manipulation benchmark in meta-world environments and assessing robustness in a settling with impaired motor capabilities. MET-ODOS again outperforms baseline methods in early training stages and shows potential for further improvement. Additionally, the model demonstrates better retention of performance when motor capabilities are partially impaired, indicating the effectiveness and robustness of fast synaptic dynamics in supporting adaptation in continuous control tasks. In conclusion, we've introduced MET-ODOS, a groundbreaking meta-reinforcement learning system that excels in rapid episodic specialization across various domains, from one-shot adaptation to spatial navigation and motor coordination. This work showcases the potential of locally tuned synaptic updates and providing evidence for the advantages of fast plasticity in artificial neural networks. Looking ahead, fine-tuning hyperparameters and integrating MET-ODOS with advanced reinforcement techniques holds promise for boosting its performance. Beyond its immediate applications, our findings prompt questions about the functional roles of similar mechanisms in biology and suggest alternative paradigms for efficient neural network control. Thank you for watching.